Introduce tonight's speaker?
I would love to. Thank you. Um, a moment ago, I was seeing Jim Lattis on my grid of people, but there's Jim at the bottom. And I wanted to comment. Jim is obviously a historian at the UW-Madison, affiliated with the astronomy department. And on my display, at least, I think very appropriately befitting a historian, Jim's video appears to be black and white. So Jim, well done, good choice. I don't know how you did that, but that's very, very appropriate. Jim is a historian of science, and many of you who have been with the club for any period of time have heard Jim speak on a number of topics over the years. Jim is constantly doing research, original research, and one of his areas of research recently has been really digging into the history of the astronomy department at the UW-Madison, a very rich and storied history. And Jim is going to present a topic tonight that I think all of you will be interested in. He's going to dig into the history of the little building that used to sit on Washburn Hill beside the Washburn Observatory, the Student Observatory. And that building has been in the news recently too. But Jim is going to go back to the origins. And so, Jim, I am delighted to introduce you, James Lattis, Director of Space Place, also professor, teacher at the UW in a number of classes, and a member of MAS for very many, many years. So, Jim Lattis, welcome and take it away.
Oh, thank you very much, John. Is the audio okay? Can somebody confirm that you can hear me all right?
You're a little
hear
low,
you, Jim.
little low.
A little low, so I should. I'm going to move up to the closer to the screen. Is that any better?
Yeah, we can hear you.
Okay. Yeah, I think the video is black and white because I have like the cheapest possible webcam. At least that's my guess. I wasn't sure if it was black and white for everybody else. It's black and white for me too. Well, thank you very much. It's nice to be invited to talk about the history of the Student Observatory, which is a part of the broader history of the Washburn Observatory that I've been working on. And I guess what I will do now is I'll share my screen because I have slides to show you, and then when I get done, I'll unshare and we can, if we've got questions or discussion or anything, we can do that. So let me share the screen first, and you got to confirm for me that you're seeing some slides here. Let's see. Do you see a title slide there on?
Looks good, Jim. Looks good.
For my slides? Okay. All right, there we go. All right, so I trust you'll tell me here if that doesn't look right. So you should be seeing my title slide there. So yes, I'm going to go do the period, although I'll talk just a little bit about the transition, but I'll do the period from the origins of the Student Observatory of that building up until the time that it was transferred away to the to MAS. In fact, it goes right back to the origins of the entire observatory. Let's see. I don't know if my pointer. Wonder if there's a way for me to. I don't know how to do that. Oops, sorry. I was hoping I could turn on a little laser pointer. Maybe you can see my cursor. For the moment,
we're seeing your cursor. We can see your cursor, Jim.
Okay, good. So you see the main building. Probably most of you have seen this famous engraving of the observatory, which dates from about 1881. This is basically the way the top of Observatory Hill looked in about 1881, and it's not much later than 1882 because of some changes that were made in the building. So right in the middle, obviously, is the main observatory where many of you have been. Just a side note, by the way, only yesterday was I informed that we are now allowed to operate Washburn Observatory again after about more than 6 months of repairs to the 140-odd year old dome. So you will be hearing about that fairly soon. And if we would like to plan a club event up there, then I'm certainly happy to work on that. So digression ended. You see the main building with the main dome, and from the very beginning, that the hill there was a complex. Really, there's the main building in the middle. On the left, you see the little Watson Solar Observatory, which is a subject of a completely different talk that we could have sometime if I haven't already done it before. And over on the right is the Student Observatory, the little observatory over on the far right, that dates from its origins from 1879. It was started, that building, by the first director of the Washburn Observatory, who was James C. Watson. But I mentioned Cadwallader Washburn first, for obvious reasons. He built the main building there, and then he hired Watson. Watson came to Madison from the Detroit Observatory, which is the University of Michigan's observatory, confusingly located at Ann Arbor. But the Detroit Observatory, there on the campus of University of Michigan, the University of Wisconsin hired Watson away from them in the summer of 1879. Watson was an interesting guy for a number of reasons, very famous in his time, one of the most famous astronomers in the US at the time. He held the record for the number of asteroids discovered by any single person. I think it was 21 or something like that. And those, of course, were in the days when you discovered asteroids by looking through your telescope and comparing with star charts, in effect, to find something that didn't belong there, and then confirming that it was moving from night to night. So an extremely laborious way of observing. But Watson was famous for that. He was also famous, and one might even say infamous, by the time that he came to Wisconsin, because of his purported discovery of the planet Vulcan, which I won't go into tonight. It's fascinating to look that up sometime if you want to. That's what the little so-called solar observatory was about, was Watson's quest for vindication of his discovery of Vulcan. Watson built the solar observatory with his own money, and he also built the small student observatory with his own money. Watson was an interesting guy. He was independently wealthy. Of course, you know astronomy. No astronomer ever gets rich doing astronomy. Watson became wealthy by doing essentially actuary work for life insurance companies in those days, and then investing in those companies that he was helping do business, develop the life insurance business. So that's where he made his money, and he spent that, some of it anyway, here at Wisconsin on the Solar Observatory and the Student Observatory. There are tales, it's more than tales, it's documented at least in a couple of books, that when Watson was at the Detroit Observatory, when he was still at the University of Michigan, that he was notoriously stingy about letting anyone use the observatory at the University of Michigan, in particular, letting it be used for astronomy classes and astronomy students. So it's always said, and it's probably true, that when he came here to Wisconsin, the idea of the student observatory, something that he did not have at Michigan, was in order that he could reserve the main telescope for himself and have a small observatory for training students. So he could divert students away, and then he could search for asteroids with the large telescope, presumably. He never explains his choices. In fact, very, very few records are left of Watson's directorship here at Washburn Observatory. Most of his papers ended up being dispersed after his death, which occurred just about a year after he was here. He actually died suddenly in the fall of 1880, and his student observatory was not finished. So it didn't really look like this. This is a blow up from that previous engraving of Watson's solar observatory, which, as I said, was not finished when he died in 1880. He was working very hard on the solar observatory. It's not clear what state the student observatory was left in at his death, but it's clear that it wasn't finished because the next director, the director who was hired to succeed Watson, namely Edward Holden, who came to Madison from the U.S. Naval Observatory to be the director of Washburn Observatory. Holden, there's letters that document Holden convincing Washburn to pay for the finishing of the student observatory. So if the student observatory was finished, as it had been said in the newspapers that it was, that was clearly not the case, because Washburn started writing checks in order to finish the little student observatory that you see. The little observatory was a small version of what was typical for larger observatories in those days, which are historians sometimes call Berlin-style observatories. It's the typical pattern that you'd expect to see, with a large equatorial telescope covered by a dome, which has a high profile compared to the rest of the building. And typically the rest of the building are wings, usually to the east and west, and often even to the north and south. In this case, in the case of the student observatory, only one to the west. And you see the wing there. So the equatorial telescope dome here, and then this transit house sticking out to the west. So it's about as minimal as a Berlin-style observatory could be. The Washburn Observatory itself is actually a Berlin style too, although it's a little harder to see that because the equatorial dome has east and west wings, and then there's a big eastern extension on the Washburn Observatory, which breaks up the typical symmetry of the Berlin style. So this was intended for an equatorial telescope, and we'll talk about what went in there. And this was intended for a transit instrument. And a transit telescope, you probably know, is a telescope that's mounted on an east-west axis. It can't point anywhere in the sky. It can only point along the local meridian. And so you can see here, you'll see some better, a little bit better in some other photos. The transit house is designed so that it can be opened. There are shutters here and here, and then symmetrically on the north side, we're looking at the south side, but symmetrically on the north side, you can open similar shutters. So you can point your telescope from due south at the horizon over here, up towards the zenith up there, and then tipping over on the other side that we can't see, you can point it north and all the way down to the horizon. So when a star crosses the local meridian, you can observe that with your meridian telescope, and there are many applications for that kind of observation. The transit house that Watson specified for Washburn is a little bit unusual in that it also provides for slits in the peak of the roof that go this way, east and west. And that could be opened up as well in order to observe along what's called the prime vertical. The prime vertical, the local meridian, of course, is the line that passes from south to north through the zenith. The prime vertical is the line that passes from east to west through the zenith at right angles to the local meridian. And so a telescope properly oriented with these shutters along the peak of the roof and on the sides and on the building as it exists today, if some of you have seen it, those are still there as well. You could open those shutters, and then a telescope could watch, see into the sky as a star transits the prime vertical. And you can make many measurements with the prime vertical that are interesting and complementary to the measurements that are made in the local meridian. So this was set up to do both, with a fairly complicated arrangement that involved not only the typical local meridian work, but also the prime vertical work over here. Here's a much better picture now that you can see. Here's the transit house that I've been talking about. So the shutters in the roof and in the north and south facing walls, but also the shutters that run east and west, and then the east and west shutters so that you get access to the prime vertical as well. This is a fairly complicated sort of arrangement mechanically, as you might imagine, in order to be able to have all these openings and have a clear line of sight from a telescope inside here in all these different directions. And that arrangement was designed by a UW engineering student who you see here. Frank Winkley is an important figure in the early days of Washburn Observatory. He worked not only on the student observatory, where he designed its dome and the transit house mechanical arrangements, but he also worked on the shutter. He actually redesigned the shutter on the Washburn Observatory, on the big dome, And then he served in its very early years, 1879 until 1881, on the staff, actually, as what they used to call the janitor. That really meant he certainly had janitorial sort of tasks, but it really meant keeping the building running mechanically in a day when that building was independent of the rest of campus. And so that meant making sure that its heating was working properly in the wintertime, and making sure that there was water accessible and that the gas fixtures were working and all that sort of thing that you would need for a building in those days. So Winkley designed these mechanical arrangements here, and only in those very early years, then he left the university and was a lifelong Madison resident, and actually pretty well known, and maintained actually connections on and off with the astronomers at Washburn Observatory until he to the end of his life in 1946. So he had a nice long life, and would appear in the paper from time to time. If you check the old newspapers online these days, Winkley will show up from time to time. One of his great distinctions is that he was one of the owners of one of the first automobiles in Madison. Back in the day when you could count the number of them on one hand, Winkley was one of the guys who was tooling around town in an automobile. And he made quite a lot of money by developing lubrication systems, pressure-fed lubrication systems that were used ultimately in cars, but also in factory equipment, and that made him quite a lot of money. So Winkley was an important Madison denizen of Madison for quite a long time, and was an important shaper of the early days of the Washburn and the Student Observatory. I'll just note that you see my notes here. A couple of us have been talking about this photo and some others, and I would love to have anybody's ideas. Maybe we should hold this till afterwards, but you might notice here, this is not visible in a great many of the photographs of the Student Observatory, but there's a tower right here. Sometimes it's there and sometimes it isn't in the photographs. I don't have a date for this photograph, unfortunately, so I don't know when this was there. This is a puzzle to me. I don't know why this tower is there. I'll show you another a piece of it in a few minutes. But at any rate, I suspect this photograph dates from the days when George Comstock was doing a research program that I'm about to talk about here. I think it was from those days because I think the dome configuration dates from about that time. At any rate, if anybody's got any thoughts about why there would have to be a tower there outside the observatory, I'd be glad to hear about that a little bit later. Well, so the first telescope to be mounted in the Student Observatory was not a refractor, not an equatorial mounted refractor, but rather the instrument in the transit house. Transit instrument measurements were really important in those days for a number of reasons, part of which involved astrometry, basically the very accurate measuring of star positions, but also timekeeping. When the sun crosses the meridian, of course, that's local noon. And when a known star crosses the meridian, a star whose position is known, you can calculate the local time from the date, because you know how far away that star will be in right ascension from where the sun would be. The first instrument then was a transit instrument, a transit and zenith instrument, manufactured by Falk and Company in Washington, D.C., and purchased specifically by Governor Washburn for the Student Observatory. So here you see an engraving of, it's probably a Falk catalog engraving. This is not a direct depiction of our instrument, but this is the instrument that Falk was selling, and this is what they had in there. So a 3-inch telescope, so you get a rough idea there of the size of the telescope, mounted in an east-west axis here, so that as it rotates up and down, it's swinging along the local meridian. The observer, here's the eyepiece right here. There's a diagonal eyepiece. They also had direct eyepieces through there. And there's a micrometer right here. So you see a filar micrometer. So there are illuminated threads that the star moves past, and you record the time of the passage of the star across those threads. And that's the fundamental measurement of an instrument, of a transit instrument like this. The instrument was used for both the measurements in the local meridian and in the prime vertical, which means that it had to rotate about its vertical axis here 90 degrees. And I have yet to see any kind of a picture that shows what that kind of arrangement was that would allow the entire instrument to pivot 90 degrees, so that instead of east and west, these pillars would be north and south. The instrument was also used both for direct observing, that is looking through the eyepiece up at a star, and for what they called reflex observations, which means you put a pan of mercury down on the pier, on an extension of the pier, and you tip your telescope up and look down into the pier of Mercury and see the reflection of the star out in the sky. And this is one way of compensating for instrumental errors, is to make a direct observation of a star and then to flip and observe the same star in the pool of Mercury. At that time, you've moved all the scales and all the bearings through an angle there. And so when you take those two readings and average them, you're averaging out a lot of potential mechanical systematic errors in the system. Another way, typical way, an additional way of reducing errors was that these instruments were typically designed to be what they would call a reversing instrument. Now, this is always pretty clear. Unlike the shifting 90 degrees to get into the prime vertical position, these instruments were designed so that when you threw this lever here, from there to there, that lifted the, right along this platform here, and these pillars, which go up to the bearings up there, lifted all of those up. And you could, so that the bearings lifted out of what are called the Ys, basically the races that the bearing sits in, lifts them clear, and you can rotate this whole thing 180 degrees and then flip the lever and let it settle down again. So you can reverse, that's called reversing the instrument. And so you reverse the instrument, and again, you might make a measurement of a star about to cross the meridian across a few threads in your micrometer, and then you very quickly reverse and make the measurement again as the star continues across the field of the micrometer. Again, by reversing, you're averaging out mechanical errors in the system. So this instrument, the Falth instrument, was used for a number of things at the Student Observatory, including timekeeping, but also establishing the latitude of the observatory by star measurements. So that's very typical work, and just the sort of thing that you would have to teach students. Students did a lot of the early work on getting this instrument calibrated. In particular, Edward Holden, unlike a lot of early astronomers, Holden was very open to the idea of letting women do not just computational work, but actual observational work and calibrating work with the instruments, actually working with instruments in the observatory. And Holden gave one of his students, Alice Sanborn here, who you see, the job of calibrating the pivot inequalities in the Falth transit. And her work was published in the first version of the publications of the Washburn Observatory. George Comstock, who was the third director of Washburn Observatory, actually came here as a student with James Watson when Watson came in 1879. And Comstock would succeed Edward Holden to become the third director of Washburn Observatory. Comstock, when he was still an assistant astronomer, used the Falth transit to determine the latitude of Washburn Observatory by prime vertical work using the Falth transit in the student observatory. So the student observatory was actually the first determination of the astronomical determination of the geographical location of the Washburn Observatory. And it remained in the Falth, that is, the transit remained a very important instrument there until it was replaced by another transit that we'll talk about in a few minutes, called the Bamberg transit in 1893. In 1893, when the Falth transit was retired, It was, again, Comstock ended up trading it to an instrument dealer in Chicago. I tried to see if I could trace that instrument at all. It disappears when traded for a handful of sextants and smaller telescopes to an instrument dealer, and it leaves Madison in about 1898. Well, the first instrument in the equatorial dome was a very famous telescope that's still around, the 6-inch Clark refractor that belonged to S.W. Burnham. This telescope, Burnham was a Chicago based, essentially an amateur astronomer in the sense that he always had a daytime job, but he was also one of the world's most famous double star discoverers. He had very sharp eyes and was very dedicated to long nights whenever the sky was clear in Chicago. And he ordered this telescope from Alvin Clark specifically so that he could search for double stars. He specified to Clark that he wanted the optical quality of the objective lens to be as good as possible. Everything else was secondary. He wanted that optical quality so that those point images of stars could be resolved perhaps into doubles, so he could continue discovering the hundreds of doubles that he was known for. That telescope operated in Chicago until Burnham came to Madison in 1881. So he bought it in 1870, so it was 11 years old when he brought it to Madison. Burnham was invited to Madison by Holden, Edward Holden, the second director of Washburn Observatory. And it was Burnham and Holden who did the first research with the main telescope at the Washburn Observatory. But Burnham brought his small telescope along, and they mounted that telescope in the equatorial dome of the Student Observatory. And here you see it, the 6-inch Clark on the mounting, also supplied by Clark, the Clark telescope mounting, on the masonry pier in the Student Observatory. Clark made this for Burnham for Chicago, for the latitude of Chicago, so about 3 degrees south of us. And so this polar axis wouldn't point up at the North Celestial Pole unless you prop up the north end of the mount there a little bit. So you can see that the mount is shimmed up there to accommodate our latitude difference between us and Chicago. So the Burnham's telescope was mounted there. Burnham eventually went back to Chicago in late 1881 and left the telescope in Madison, apparently on loan. At least Holden describes it as being on loan. I don't think he was holding it hostage. I'm not entirely sure. Holden actually wanted Burnham to come work for the university at Washburn Observatory. Burnham did not want to do that. Burnham left the telescope here, as I say, ostensibly on loan. And then in early 1882, Holden reports that the university has agreed to buy the telescope from Burnham for the sum of $1,200. And apparently the new cost of this telescope from Clark when Burnham bought it in 1870 was $800. He must have made some improvements to it, I suppose. For whatever reason, we became the owners of what is now a very famous telescope in early 1882. And it was in the Student Observatory then for quite a long time and played an important role in research that I'm about to mention to you. The image that you see here, this tube is not the original Clark telescope tube. You can see rivets in it. This is the steel tube, which replaced the wooden tube in about 1908. And the steel tube is what we still have today on the roof of Sterling Hall. That's the tube, you'll see it up there. The wooden tube ended up at the Adler Planetarium, as I'll describe in a few minutes. So Comstock was really the third director of Washburn Observatory was really the one who did the first significant astronomical research at Washburn Observatory. Some of that research was work on double stars with the 15.5-inch telescope in the main dome. But some of that work, some of the most important of that early work of Comstock's was done with the Student Observatory using the Burnham telescope. And that work was investigating two phenomena that are extremely important to positional astronomy, extremely important to determining the true positions of objects, specifically usually stars, most fundamentally stars, I guess I should say, in the sky. And those two effects are atmospheric refraction and a phenomenon called the aberration of starlight. So atmospheric refraction, these days we don't have to worry about that too much because our smart telescope mounts know how to correct for atmospheric refraction. But in fact, if you calculated geometrically where the sun is at this moment, where we see it setting here, you would find that geometrically the sun is already well below the horizon. But light doesn't travel in straight lines when it passes through the Earth's atmosphere. And so the refraction of the light through the Earth's atmosphere gives us the appearance of the sun still above the horizon. Atmospheric refraction tends to move images of things in the sky toward the zenith. But that effect is strongest near the horizon, and you can see it's quite strong near the horizon because it's a considerable fraction of the degree here that the sun has been, the image of the sun has been raised above the horizon. So atmospheric refraction is important to quantify because you measure a position of a star over here. That's not its true position. That's its refracted position through the Earth's atmosphere. The other phenomenon that shifts, well, another phenomenon that shifts positions of stars is called the aberration of starlight. This is a much smaller effect, at least smaller than refraction near the horizon. And it shifts images on an annual cycle. And it doesn't shift them very much, but enough that you'd be pointed in the wrong place in a lot of cases, about 20 arc seconds of motion. And this happens because of the Earth's motion, because of the Earth's orbital motion around the sun. And this little drawing here is trying to illustrate that. Here we have the Earth, and on a station, if you were on the sun, let's say at the North Pole of the sun, you would point in this direction to see this star. But on the Earth, with the Earth in motion, you have to tip your telescope through a small angle here in order to be able to center it in your telescope. And that's because of the finite speed of light. And the amount of this angle is determined by the ratio of the speed of the Earth's orbital motion to the speed of light. So the finite speed of light produces a small shift. I should say the finite speed of light and the Earth's orbital motion produces the small shift in the stars. When the Earth is going this way, it shifts the star that way, and then around on the other side of the Earth's orbit, when the Earth is going around that way, it's going to shift the image of the star the other way. So the apparent image of the star is going to go back and forth like this. It's actually going to make a circle around here that is about 20 arc seconds in radius. So if you want to get an accurate position of a star, if you're measuring stars to accuracies of fractions of an arc second, then you've got to know about this effect in some detail. Well, this was actually discovered in 1729 by James Bradley in England. And in fact, his discovery of this was the first direct evidence of the motion of the Earth's motion around the sun. So it's the shifting, the small shifting of the position of the stars in the sky wouldn't happen if the Earth weren't orbiting the sun. So next time you're having a beer with a geocentrist, ask them how they would explain the aberration of starlight. 99 out of 100 of them won't have heard of it. At any rate, it's an essential phenomenon for understanding if you're going to do accurate astrometry, accurate measuring of star positions. So Comstock settled upon a novel method of measuring both of these effects. Normally, these effects would have been measured by something like a transit telescope, looking out the slit of the transit instrument and measuring as accurately as possible the position of a star, and then doing that through the year. But there are many errors involved in doing that, which had to be calibrated for it. Comstock realized that there was another way to do this, which involved not an absolute measurement of the star's positions, but a relative measurement, essentially a differential measurement between the positions of two stars. So for example, if you could look at a star that's near the zenith and a star that's near the horizon and measure the angle between them, which is going to be many degrees, like close to 90 degrees, and then measure the angular separation between those two stars when, say, both of them were at 45 degrees above the horizon, you get different numbers because of the refraction. And if you can measure that angle between those objects directly, that big angle of 90 or so degrees, if you could accurately measure that, then you could measure the refraction effect without any reference to the horizon and the zenith and all of the absolute type of measurements that a transit instrument is trying to make, with all the attendant errors in there. So Comstock settled or learned about a device that had been invented by Maurice Loewy. Here he is, right here, the University of Paris astronomer, who put together a device that involved two reflecting surfaces, the sides of a prism. And depending on the angle of the prism here, when you look right up at the edge of the wedge of the prism and you see one star here and one star there, those stars are actually separated by a much larger angle because of their reflection off the faces of the prism. If you use a 60-degree prism, then these stars will be 120 degrees apart. If they're 120 degrees and an arc minute apart, then when you look at those two stars in your filar micrometer at the end of your telescope, you'll measure their separation to be a minute of arc apart, a separation, an angle of a minute of arc. The Loewy device essentially subtracts 120 degrees from the angular separation of the two stars in the sky. So this is what Comstock decided to do to make a new determination of the values of atmospheric refraction and the aberration of starlight using a very novel arrangement, his own version of a Loewy device that he had designed and made by John Brashear of Pittsburgh. He had Brashear make prisms with a prism with a 60-degree angle. It turned out, now those surfaces have to be optically flat, and it turned out Brashear had a great deal of trouble making an optically flat face on a 60-degree prism because the thermal properties of it were completely crazy. Eventually, they switched to mirrors, but let's stick with the idea of the prism for just a moment. This is the prism mounted at the front, in front of the objective of the 6-inch Burnham telescope. So there's a prism face here and a prism face here, and we're looking this way through the telescope. So this gadget, you'll see it in a minute, is mounted. Comstock called it a reel because it's a cylindrical thing, mounted in front of the telescope. Brashear eventually changed this to mirrors because he could make those flat, and then it turned into a mechanical mounting problem to make sure all the faces were 60 degrees apart. But they solved that okay. We're looking through the telescope, and in front of the objective of our telescope, we're seeing the faces of mirrors or prism faces. So we're seeing a star off this way, the light from a star over here, and the light from a star over there. They're 60 degrees each one away from the center line of the telescope. So we're looking through the telescope at the faces of this prism. And that's basically the way Comstock made the measurements, by seeing these stars, which would appear in the same place if they were exactly 120 degrees apart. But if they're not exactly 120 degrees apart, then your micrometer will show you how far apart they are. Up here, this is the so-called reel, the cylinder. And inside there, you can't really see them, are the faces of the mirrors that they eventually used. So this assembly holds this prism in front of the Burnham telescope. It has to be controllable from the observer's end here. It needs to be rotatable, so it can rotate about this axis. And it also needs to rotate about the optical axis of the telescope. So his controls down here can also make this thing rotate in a circle like this, so that he can get the two stars that he needs arranged in the field in the view of his micrometer down here. So this whole mounting getup had to be built for the telescope, and all the controls and stuff down for the eyepiece end and the linkages in between all had to be built special. And they were built by Fouth, the same company we were just talking about, Fouth and Segmuller, who was one of their principal mechanics and opticians there in those days. Fouth and Segmuller actually had the Burnham telescope up there in DC to fit all these things on, and they got the optics, basically the prisms and mirrors, from Brashear. So Comstock started doing an observing program here of stars that are on the order of 120 degrees apart, which explains this very mysterious picture, one of the few of the student observatory with the dome open. You'll rarely see a dome like this where it's just complete half open. It's a hemisphere there. But of course, to measure these stars that far apart, you need to see about half of the sky. So Comstock had to rebuild the dome of the student observatory into two concentric hemispherical shells. So you see the one inside here, and then the other one larger than it and stretching around, both of them rotating around the vertical axis through the pier here, so that by pulling, this was the arrangement until the modern renovation of the dome, by pulling these boards here, you could move these dome hemispheres around on rollers in order to see an entire half of the sky, so that you could see stars that were about 120 degrees apart. So this was a major rebuilding of the student observatory dome. And I have a note here to remind myself, I mentioned that mysterious tower a little earlier. I'm pretty sure what we have here is a little bit of that tower sticking into the picture. The rest of the tower is missing out here. So there seems to be a small platform there. Just pointing out the little clues I have in case anybody has any thoughts about what the heck is going on. Because it was there while this program was in effect, I suspect that it has something to do with his work here. So I don't know whether it's some kind of calibration, something to point the telescope at. At any rate, here we have this unusual picture of the student observatory there with the hemispherical shell domes. Hemispherical shells. Well, so what did Comstock come up with? After several years, really about 2 years of constant observing, measuring many pairs of stars and measuring their separations and calculating where they should be based in the sky, he was able to come up with a measurement of atmospheric refraction as a function of altitude above the horizon, which was the first determination of that outside of Europe. All of the tables that astronomers were using for that in those days had been compiled in Europe, and the favorites of astronomers were the ones done at the Russian observatory at Pulkovo in St. Petersburg, Russia. There was actually some question about whether you could just take the results done at Pulkovo and expect them to be the same everywhere on Earth. And part of Comstock's contribution here is that he's done this again in a completely independent method in a completely different place, now in North America rather than in Russia, and showed that, among other things, the surface gravity, which would be different depending on where you are on the Earth, your latitude, among other things, and your altitude above sea level, does not produce a big effect. He also came up with a new empirical formula for the refraction correction that could be used in place of tables. So instead of having a lengthy table where you looked up your refraction correction, he basically had a little algorithm, a little formula that you could plug in and create, find what the atmospheric refraction should be at that position in the sky. So that was a significant contribution to both the science and the practical use of the correction for atmospheric refraction. In the case of the aberration of starlight, which had been measured by a number of other methods, he basically confirmed those independent methods and came to the unexpected conclusion that his result was actually more consistent with everybody else's results if he did not try to correct for what they called the personal equation, the idiosyncratic error of human observers, which in those days was tracked and measured rather carefully. He didn't know what to make of that, but he honestly mentions it in his report, that his number is better if I don't correct for the personal equation. A little bit of a mystery as to what's going on there, but one of a number of measurements of the aberration of starlight, which becomes important because if you know that number well, and if you know the speed of light well, which in the same days in the 1890s was being measured as accurately as possible in ground-based laboratories, with those two quantities, you can calculate the astronomical unit, the distance of the Earth from the sun, the radius of the Earth's orbit. And this was a much sought and much needed number. You perhaps have heard of the quest to measure the transits of Venus, the goal of which was to determine the astronomical unit. And various other ways of trying to get at the astronomical unit, which is then the baseline for parallax measurements and thus affects how big we think the universe in general is. It's a fundamental yardstick for astronomers, and the aberration of starlight is a number that you can use as one method to get at the astronomical unit. So this was the first significant research program really to come out of Washburn Observatory, and it was done there in the Student Observatory with the Burnham telescope. Well, I mentioned that the South Transit lasted until about 1903, when Comstock removed it and replaced it with a new transit instrument. This instrument that you see here, which came from the instrument maker Carl Bamberg, not in Bamberg, Germany, but in Friedenau, which is near Berlin. It's just the instrument's maker's name is Bamberg. This kind of transit telescope is called a broken transit. You'll notice that there's the objective lens here and the tube, but there's no tube coming out the other end. There's no eyepiece down there because there's a prism right here at the vertex of the whole instrument that bounces the light out to the side. So you can tip the transit instrument through its entire range of motion, and you can keep your eye right there the whole time and not have to move around with this end of the telescope. So it's called a broken transit because the optical path is broken, so to speak, is bent at 90 degrees there. So this instrument was used for all the things that the older Fouth instrument was used for, including measurements in both the local meridian and in the prime vertical. It was used for the time service. It was used also for reflex measurements, but notice how much easier a reflex measurement would be. That would mean that you'd put up a little pool of mercury right here and tip your telescope down. With the Fouth instrument, you'd have to stand on a chair to look into the eyepiece over here. But with the broken transit, no problem. You're right here all the time. So the broken transit is a big improvement for the observer in that kind of situation. Comstock was very fond of the instrument and considered it the finest that he had ever seen. Also, this instrument, like the Fouth, is a reverse, can reverse. Most of them could. Here's the lever here that's flipped over to that side, which would lift. In this case, right here, lifts the telescope out of the pivots, and then you swing it around and throw the lever back, and it settles back in there, flipped 180 degrees. The big transit instrument in the main observatory, which I'm not going to talk about, could also reverse. It was a much bigger instrument, and reversing was a much harder process than it was with an instrument this size. This telescope, had we been doing this at Space Place, I would send you all through the door so that you could see this telescope on exhibit over at Space Place. We have it sitting right there in our exhibit area. So next time you're down at Space Place, you can take a look at Comstock's Bomberg telescope. An unusual aspect of research at the Student Observatory was really just pretty much a one-time shot. In 1897, in September of 1897, the UW history professor Orrin Libby was an amateur ornithologist and hit upon the idea of trying to measure bird migrations at night. You can measure them in the daytime just by having some students sit around and count how many fly by, but how many are flying at night? The same number, more or less, pretty hard to tell. Libby proposed to measure this by looking at the disk of the full moon, and he recruited help from Washburn Observatory, and specifically the astronomer Albert Flint, who was the Meridian Circle observer there during the Comstock days. And they, along with an assistant named Winslow Mallory, on these nights in September near the full moon, they observed during the night and counted the number of birds that they could see cross the disk of the full moon. And using that as a representative sample of the entire sky, they then calculated what fraction of the moon, of the area of the sky the moon was, multiplied by the right factor, and came to the conclusion that at that time of year, at least, there were about 9,000 birds per hour visible from Madison, crossing the sky visible from Madison. That was the first time anybody had ever come up with such a number, such an estimate of bird migration at night. I'm not sure how that compares with the daytime numbers. He published these results, and he probably talks about that. So that was kind of an unusual aspect of research at the observatory. But after that, we don't see much research done at the Student Observatory. Right around 1900 seems to be when any research with the Student Observatory pretty much ended, until another telescope ends up there in the Student Observatory, which I'll tell you about in just a moment. The Burnham telescope was on the Clark Mount until 1927, when Joel Stebbins had a new mount designed for it. A new equatorial mount was designed by a UW machinist whose name was Oscar Romer. And it was really built as a prototype for the new mounting that Stebbins wanted to put on the 15.5-inch telescope in the main observatory. So in 1927, the Clark mount was replaced by a new mount, which I'll show you in a picture here. Also, the wooden tube had been replaced, as I mentioned earlier, by a steel tube in 1908. So by 1927, both the Clark mount and the original wooden tube from Clark had been replaced, and these parts were of considerable interest to the astronomers who gathered in Madison in 1927 at one of the meetings of the first meeting of the American Astronomical Society in Madison. So here they all are, not a huge meeting in those days, gathered in front of Washburn Observatory. And they're posing in front of the observatory. In front of the group photo is this, what looks like a stovepipe here, but that's the wooden tube from the Burnham telescope, which apparently was trotted out as sort of a relic to be to take its place in front of the gathered AAS astronomers. And this is the Stebbins's dog, whose name was Tico. And Tico's either very well trained, or Stebbins had put a ham sandwich or something inside the telescope tube. I'm not sure what Tico is looking at there, but he's posing very nicely. There are a number of people in the picture here. I'm not going to go through all of those. You can see a few, though, that are easy to spot. There's Joel Stebbins, and there's George Comstock, who was retired by then. This is Huffer, C.M. Huffer, Morse Huffer, whose name will come up shortly here, Huffer in 1927. Here's down here is Edwin Frost, who is the director of Yerkes Observatory. He was up here for the meeting. Here's Otto Struve, who would succeed Frost as director of Yerkes Observatory. Over here is Philip Fox, who in those days was director of the Dearborn Observatory at Evanston, Illinois, of Northwestern University. And Fox would, shortly after 1927, leave that job and take a job as the first director of the Adler Planetarium, which was built in about which opened in 1930. Another figure that we should mention here is J.W. Fecker, right over here, who was a telescope maker. He was the Clark of his day, telescope maker from Cleveland, and Fecker will come up in just a moment too. So when Fox opened up the astronomical exhibits at the Adler, he wanted Burnham's telescope represented there because Burnham had come from Chicago. It was a big deal for Chicago astronomical history. And Fox had been up here and knew that Stebbins had the wooden tube and the Clark mounting, and he asked for those two artifacts to make into an exhibit at the Adler Planetarium. So those things were part of the opening exhibits at the opening in the Adler Planetarium. Stebbins up here sent them down to Fox at the Adler on loan, and they've been there ever since. So the tube and the mounting are both still at the Adler Planetarium. They're not on display, but they are there in their holdings. And I've been down there to see the tube at least, and it has the little tag on it that has a big L on it that I'm told means it's on loan. So they know it too, that it's on loan, but we're not going to ask for it back right away. Here's the new mounting that replaced the Clark mounting that was designed by Oscar Romer. This was quite an innovation for its time. The Burnham telescope was mounted on this, so it's a small mounting. The same mounting is still on the roof of Sterling Hall, though it's been reworked at least once since then. But it was a prototype for the larger mounting and had many innovations for its day, including a wheel right here that you could turn to slew the telescope on the polar axis. And it also had an integrated hour angle dial here so that you could read the hour angle of the polar axis directly right there without having to look at the setting circles. And it had electrical controls to speed up or slow down the clock drive. So you could do fine pointing in east-west, fine pointing in the RA, guiding basically in the RA dimension. So this was a highly telescope. These are all the latest things, electric motors and electric controls. This was a very advanced mount for its day. And all of these innovations made their way into the Washburn telescope mount as well. To go on this new mounting, Stebbins ordered a new telescope. Basically, he ordered a 10.5-inch objective lens from Fecker, J.W. Fecker, the guy that was there at the 1927 AAS meeting. This is the 10-inch refractor here that replaced the Burnham telescope on the new Romer mount. This was a new generation sort of telescope objective. It was photographically corrected, not visually corrected. The achromatic correction here was for photographic work, although photographic work is probably not what Stebbins did with it. He actually was doing photometry. He was testing photometers at this end of the telescope, and photometers don't need a fine image. In fact, you often use an out-of-focus image with photometry in that day. And so Stebbins economized by having Fecker only really partially perfect the optical surfaces there. So I've never been able to test it. We still have this objective, and in fact, we still have the tube in storage. So we could reassemble this telescope, but I think there would be little point in it because this objective will probably not produce very good images. It's a light bucket, a refractor form of light bucket. Well, at this time, by the time we get to about 1930, the dome was still in the configuration that's the semi-dome configuration that Comstock had converted it into. It had not been converted back to a conventional slit opening sort of dome. And that apparently happened in early 1929. It's not really very well documented, but you can see the work in progress right here. Notice there's no tower, by the way. You can see the work in progress. And here you can see what I'm told is a 1929 DeSoto coupe. And so that seems to be, that helps date approximately when this work was going on. So the dome was converted back to its old configuration, and so now it's back to a conventional slit right up here. And that's the configuration the observatory was in right up until the end of its activity. In 1958, the astronomers moved to the Pine Bluff Observatory, so Washburn was no longer a site for research. The astronomy department moved its offices away from the observatory and up to Sterling Hall. So suddenly up on Observatory Hill, things were pretty quiet. And the student observatory was certainly not needed at all anymore. And it's at about that time that C.M. Huffer, Morse Huffer, comes back in to our story. Not that he was very prominent before, but I did show you his picture earlier there in 1927. Morse Huffer was one of the founding members of the Madison Astronomical Society way back in the 1930s. And for details on this, you should see John Rummel's History of the Madison Astronomical Society. But Huffer must have been the key to the transfer of the old student observatory building to the Madison Astronomical Society. And in August of 1959, the state legislature approved the transfer of the state property, the building of the Student Observatory, to this private organization, the Madison Astronomical Society, authorized its removal from the Hill and its transfer to the club, which then happened in 1960. And again, John's history of MAS describes this process of which is more than just moving, but involved, uprooting this building out of its foundations and moving it to Fitchburg. So here, just a picture of the dome getting ready to turn down Charter Street and depart out to Fitchburg to the new site there in at the Bjorkston Labs property, where it was renamed after one of the donors, the major donor of the move, Oscar Mayer. It was named the Oscar Mayer Observatory and was the MAS Club Observatory out there until 1984, when the move out to what's eventually YSO was in progress. After the club stopped using it, the building was pretty much empty for quite a few years, and so it really leaves the UW picture in 1960, which is why I've nominally stopped my talk there. But just to give the epilogue, most of you, I think, already know this, that building still sits where it was moved in 1960, but now is owned by Promega Corporation, where their educational institute, which is called the Biopharmaceutical Technology Center, their institute operates it now as an educational observatory. Several of us have been out there and observed with it, and they have basically Bill Linton, the owner of Promega, put a lot of money into refurbishing and remodeling the observatory and putting a modern telescope, well equipped, up here, and rebuilt the mechanicals of the dome so it's remote controllable and all kinds of great things, with a very nice observing room in what used to be the transit house over here. So that's the path from 1879 up until where the observatory has landed at the present day. And I've talked for a little bit longer than I meant to, so I will wrap up right now, and I'll be happy if anybody has any questions or discussion or can explain that tower to me. I'd love to hear about it, but thank you very much for your attention tonight and for the invitation to talk to you tonight.
Hey, Jim, regarding the tower, I'd be surprised if you haven't thought of this, but the thing that occurred to me as you were showing the pictures is that that tower positions that little platform, a little bit to the southwest. It's kind of low and out of the way. Was Comstock's prism setup, did that setup require some kind of calibration that would have benefited from having some kind of an instrument sitting on that tower for purposes of calibration? And then once you're finished calibrating, you put the instrument away. And after Comstock's setup was no longer being used, the tower was removed?
Yeah, that makes perfectly good sense. And yeah, I think the calibration is one of the obvious possibilities, but I don't know what that would mean. I'm still not sure what that tower would accomplish. It would be too close to the telescope, to image anything there. I mean, whether there was perhaps a light source in there or something, I don't know. But yeah, calibration is certainly one possibility, but that's just kind of a general example. I'd have to guess that's what it is, but I don't know what it is. It's not big enough to climb, so it's not for climbing up there and wiping off the lenses or something along that line. So yeah, quite possibly a calibration thing, but I don't know in any detail, or for sure if that's what it was.
Well, with respect to the measurement of atmospheric refraction, I would imagine that is influenced somewhat by meteorological conditions. I do know they made meteorological measurements at the observatory. Were those used in coming up with those correction equations at all?
That's a really good question. I don't remember whether, say, the temperature or humidity are parameters in Comstock's formula. I kind of suspect not, because most of the atmosphere that's affecting you is not really anywhere near you. So what the temperature and humidity conditions are going to be along the line of sight out to the star maybe aren't particularly well represented by what it is right at the observatory. But it might be. That's a good question, and I don't remember right off. I'd have to look. You are right, of course, that making meteorological measurements was a major part of the observatory's activity for many, many years, until there was a weather bureau. And the observatory was the official record for, well, I should say an official record for temperature and humidity measurements and wind speeds and things like that. And they were regularly consulted by somebody who wants to know what was the coldest day in 1892 or something. So they did have that, and he would have had access. He would have had that kind of data to figure in there, but I don't remember whether that's in the analysis. Like I said, I'm not so sure it would make sense to have just those very local numbers, since you're looking through a whole path along the Earth's atmosphere. But next time I take a look at that, it's in the publications of the observatory. I'll take a quick look at that and see whether if he talks about that.
Yeah, I'm kind of digging Jeff's humor about thinking it might have been a bird feeder due to the some of the observations involving birds and things. And that's kind of the funny thing about historical mysteries sometimes, is sometimes things like that are the answer, and you would never realize it.
With respect,
that'd be funny.
With respect to the birds, I do have an interesting story. When I was a graduate student in zoology, one of the prominent zoology professors was Jack Haleman, who studied ethology, mostly of birds and the behavior. And I remember hearing it at one point in the autumn, he invited a group of students to come out and make observations of the birds flying in front of the full moon. Unfortunately, he apparently either misread or didn't really look up to see when the full moon was going to be, because there was no moon to see the birds against.
Oops.
But they probably had some beer and enjoyed themselves.
I've got a couple of birder friends, people who are very fanatical, as many birders are prone to be. And the Audubon Society and other societies still do full moon nighttime transits of birds as methods of counting, flock size at night. So that was evidently a pioneering effort by that astronomer, because that's as far as I know, that's common practice these days.
Yeah, I guess I don't know whether he was the first one to try that, although it sort of sounds, I've read his article, it sounds like nobody else has done that. He was really not an astronomer. He was a history professor and amateur ornithologist, who did publish a number of things in ornithological periodicals, but he remained a history professor while he was here, and then he moved, I forget now, right around the turn of the century. He took a job, apparently he came into conflict here with Frederick Jackson Turner, who was somebody not to be reckoned with, not to be messed with, on the UW campus, and he ended up moving to a faculty position in North Dakota, where I think he continued his ornithological work. So yeah, that Orrin Libby is a fairly well-known figure from that period, right around the turn of the century.
Well, are there any more questions for Jim?
I will stop screen share if we're if nobody needs to go back to any other images there.
Yeah, on behalf of the Astronomical Society, once again, thank you so much, Jim, because sometimes we take for granted how lucky we are to be near such a great university and to have all this access to this information and research that you have about the history of the research that's happened at UW-Madison. So on behalf of the club, thank you so much for your time and your expertise in this very great presentation. Well done, bravo.
You're welcome. Thanks for your patience. It went a little longer than I expected.
Well, so did the business meeting, so.